Standard AI often fails when deployed in the real world, sometimes with hilarious consequences, as with Long Cow here, sometimes with very serious consequences for health or with biases, but quite often with consequences for businesses that cost them money and trust. Gartner say that about 85% of AI deployments fail, and a big reason for this is going to be that people are using standard AI for something it's not designed to do. When you're deploying something into the real world, often what you need is not just prediction, but prediction upon intervention. And this is what causal AI is designed for. So here I'm going to show you a really simple demo of causal AI using our flagship platform causaDB side by side with standard AI to show why you need causal AI if you want your AI to work in the real world. Our causaDB platform is a general purpose DevOps platform for causal AI, so it can be used for many use cases across industries. But here, for this demo, I'll show you one example use case of the optimization of heating control systems for commercial buildings. I'll show why it's important that causal AI is used for this problem and not standard AI, and we'll compare those two approaches head to head. You'll also see how causaDB can be then used in an end-user application. The problem of heating control is one of many interesting problems for AI because large buildings often need to be effectively preheated or pre-cooled ahead of time. Now, in this example, we're going to use actually a simulated dataset, but this is by design because it allows us to simulate deployment into the real world, which is something that you can't do with historical datasets. So our dataset contains variables such as day, outdoor temperature, the indoor temperature, the overall energy usage of the building, and then the heating setting of the HVAC, the heating and ventilation system. This is a thing that we're trying to optimize. So let's have a look at the data here. We read the data in, and it looks like this. So we can see that the outdoor temperature and indoor temperature fluctuate throughout the year, where ideally we'd want the indoor temperature to be constant throughout the year. So our goal is to estimate the best heating setting that we can use on each day to maintain a target temperature throughout the year. So first, let's have a look at a standard AI approach to this of predicting the heating settings from the outdoor temperature and the target indoor temperature. We've implemented this in XGBoost, a good general purpose algorithm, but the results that you're going to see apply equally to any kind of non-causal AI. It doesn't matter if it was reinforcement learning, a neural network, and it doesn't matter how many neurons or how much data you have, the same results will apply. So we fit a model here where we predict the heating setting from the outdoor temperature and indoor temperature. So we fit a model and see that it performs very strongly when you validate it on an unseen test set, which is a common approach for how you validate standard AI. So this algorithm traditionally might be considered ready for use in production. But because we're using a simulated dataset where we know the data generating process here, we can actually simulate how the algorithm would perform when deployed in the real world. So we've simulated an entire year's worth of outdoor temperature. So now we can set the target indoor temperature and see how the model performs. So we do that here by setting the target temperature to 18 degrees. Now, what you can see here is the recommendations from XGBoost actually applied and simulating the action and seeing what the indoor temperature is that's achieved. And as you can see, it performs really poorly in deployment despite the fact that it did really well on the test set. It's about 2 degrees off on average and it's not very stable. Now for AI that works in deployment, we really need causal AI. So now I'm going to use causaDB to show how we can solve the problem. So there are 3 main steps to fit in a causaDB model. It's really simple. First, we register the dataset with causaDB, and in this case we're using a local file from pandas, but you could also pull this from a SQL server such as BigQuery, or even secure streaming with data lakes. Next, we define the model and its causal structure. We don't go into the details here of how you define causal structures, but we've got information on that in the documentation on the website. But you can also define the model with our Model Builder app with a no-code drag and drop interface. So I'll quickly show you this before continuing with the demo. So I'm not going to talk about this in detail, but here's our no-code interface. You can very easily bring variables in and you can very easily connect them up to allow cause and effect to be learnt if it exists between two variables. And then it will generate the code. You can copy the code and paste it in. It's as easy as that. Once we've defined the model, we can train it. And now we can query the trained model in a number of ways to extract useful things such as the causal effects, attribute the root cause of an outcome, simulate actions, and lots of other things. But the focus of this problem is on finding the best action to achieve our desired outcome. For this, we need to use causaDB's find actions function. So we set the target indoor temperature. We say what we want the action to be on, and here it's the heating setting. And we say currently the outdoor temperature is 16 degrees. So let's run this function and see how the model performs. So you can see it's recommended a setting of 54.63 and it's achieved an indoor temperature close to the 19 degrees that we wanted. So this is what we're looking for. So now let's compare the annual performance of causaDB with XGBoost, again simulating what would happen if we now deploy these both in the real world and compare them side by side. So you can see that the causaDB model massively outperforms the XGBoost model in deployment. Also, we can look at the mean absolute error under causaDB, and it's about 10 times reduction in the XGBoost model. It's also significantly better than the original human operator. Now, you can also see the economic impact of this. The cost reductions are over 300k per building per year compared to the manual and standard AI approach. So now what we can do is take a look at the live app that we can very quickly deploy from this trained model. And this app might be, for example, what a building manager might have access to, or it might be automated to know the daily heating settings that we want. So let's have a look at that. So here you can see a really quick Streamlit app that we've put together, and we can go in and say, what's the target building temperature? And it might be kind of 17.8 degrees. What's the current outdoor temperature? And it might be 12.2. Okay, so now we've set that, we can go and have a look at how standard AI does, and we can look at how causaDB does. And now we can check the difference between them. And again, you can see that causaDB does really well, whereas standard AI fails in deployment. So this has been a short introduction to using causaDB for smart building energy management. As I say, it's a general purpose platform and can be used across industries. Now, the code in this example is openly available on our GitHub, and you can check out our site and documentation for more information.